Okay, so hello everyone. In this video, we will discuss Hamiltonian graph or Hamilton graph. Now, for us to consider a graph as a Hamiltonian graph, it should consist the two. We have a Hamilton path and a Hamilton circuit. If we only have a Hamilton path, but we do not have a Hamilton circuit, then it cannot be considered as a Hamiltonian graph. But if we do have a Hamilton circuit, then it follows that we also have a Hamiltonian path, and that means we also have a Hamiltonian graph. So let us define Hamilton path and Hamiltonian circuit. So when we say Hamilton path or Hamiltonian path, it is a path that visits each vertex of the graph exactly once. So we will be using all the vertex in a particular graph at exactly once. When we say Hamiltonian circuit or Hamilton circuit, that means it is a path that uses each vertex exactly once and return to the starting vertex. So it's basically a Hamilton path that goes back to where it started. Now, for us to understand this concepts, we will be using the figures or the illustrations that you can see in your screen. So let's begin with figure A. Now let us try to identify if this is a Hamiltonian graph. So first, let us check if we can have here a Hamilton path and a Hamilton circuit. Let's begin with Hamilton path. So again, Hamilton path, that means you should be able to use all the vertices once. Okay, so if we will start from vertex A, okay, vertex A, we can go to vertex B. From vertex B, we can go to vertex C. From vertex C, we can go to vertex E. From vertex E, we can go to vertex D. So since we have used all the vertices in this graph, then that means it has a Hamiltonian path. Now, let's check if we can have a Hamilton circuit. So again, Hamilton circuit is just a Hamiltonian path that goes back to where it started. So we end here from D, we can go back to, or we can continue to vertex A. So that means we started from vertex A, we ended up with vertex A. So we have here a Hamilton circuit. Now, if it contains Hamilton circuit, it follows that it also has a Hamilton path and therefore it is considered as a Hamiltonian graph. Now, it's up to you if you want to start with vertex B, vertex C, vertex D, or vertex E. That is up to you as long as the conditions will be satisfied. Now, let's go to figure B. Okay, let's find a Hamilton path first. So I will be putting check here now since this is a Hamiltonian graph. So if I will start in vertex A, I will go to vertex B, I will go to vertex C, and then I will go to vertex D. So I have used all the path at all the vertices at exactly once from vertex A to vertex B to vertex C to vertex D. Now that will be the same if I will be using vertex C, from vertex C to vertex D to vertex B and to vertex A. So I have used all the vertices in the graph. That means this graph contains a Hamiltonian path. Now what about a Hamiltonian circuit? Let us try to check if we can find a Hamilton circuit in this particular graph. So if I will start from vertex A, I go to vertex B, I go to vertex D, go to vertex C, alright, go to vertex B, and I will go back to vertex A. So yes, I can go back to vertex A. However, I have used vertex B twice already, and it violates our conditions. Since for us to have a Hamiltonian circuit, we can only use each vertices once. Okay, so let's find another path since this is a trial and error process. Another circuit rather. So if I will start from vertex C to vertex D to vertex B to vertex A, I cannot go back to vertex D. So that means whatever we do, we cannot find a path wherein we will go back to its starting point. So in this case, this graph only contains a Hamiltonian path but do not contain a Hamiltonian circuit. Hence, this is not a Hamiltonian graph. Okay, now let's go to figure C. So let's look first for a Hamiltonian path. If I will start in vertex A, I go to vertex B, and then after vertex B, I have two choices. I'll go to vertex C or I'll go to vertex G. Suppose we will go to vertex C and then we will continue to vertex D. So we ended up with vertex D. We weren't able to use vertex G, E, and F. So that's not a Hamiltonian path. Now if I will go to from A to B to C to E to G, so we won't be able to use vertex F and vertex D. That's another thing that do not satisfy the condition. Now, if I will use B to G to E to F, so we'll not be able to use vertex C and D. So we couldn't find a Hamiltonian path in this particular graph. All the more for the Hamiltonian circuit. So since this graph do not contain a Hamiltonian path and a Hamiltonian circuit, therefore this is not considered as a Hamiltonian graph. Now, as I have told you, Hamiltonian graph is a trial and error process. Now, we'll be using the Dirac's theorem to find out if a particular graph contains a Hamiltonian circuit or a Hamiltonian path, or if we can consider a particular graph as a Hamiltonian graph. Okay, so look at this figure below this one. Consider this one as a connected graph with at least three vertices and no multiple edges. So when we say no multiple edges, that means there should only be one edge that connects to the two vertices. Just like here, A and B. There's only one edge that connects to it. No, so we cannot add another edge in here. That will be a violation to the condition. So we have here, this is our connected graph with at least three vertices. Now let n be the number of vertices in the graph. If every vertex has a degree of at least n over 2, then the graph is Hamiltonian. So let us count how many vertex are there or how many vertices are there in this graph. So we have 1, 2, 3, 4, 5, 6. Right, now from Dirac's theorem, each vertex should have a degree of n over 2. So n here denotes the number of vertices. In this case, the number of vertex that we have in our graph is 6. So we'll have 6 over 2. That gives us 3. Therefore, each of these vertices should have at least 3 degree of vertex. Alright, so the degree of vertex should be at least 3. Now, when you say degree of vertex, you should be counting or you just have to count the edges that is connected to that particular vertex. Okay, so we'll have the degree of vertex A. Now, we have for vertex A, we have 1, 2, and 3. Three edges that is connected to it. Now we'll go to the degree of vertex B. So we have 1, 2, 3, and 4. There are 4 edges that connects to vertex B. Now, let's go to the degree of vertex C. So we have 1, 2, 3, 4. Next, we have the degree of vertex D. So we have 1, 2, 3, 4. Still 4. Now we'll go to the degree of vertex E. We have one, two, three, four, still 4. Next, we have the degree of vertex F, that is 1, 2, and 3. Now, by direct theorems, we have here, based on this graph, each vertices should contain at least 3 degrees. So here we have 3, 4, 4, 4, 4, and 3. That means it satisfies our condition. Therefore, by using direct theorem, this one or this graph is considered as a Hamilton graph. Okay, so all you have to remember, if a graph is a connected graph with at least 3 vertices, then you just have to count the number of vertex that a graph contains, then divide it by 2. The result will be your basis, or will be the minimum number or the minimum degree of each vertex. Okay, now do not confuse yourself with the Hamiltonian graph to the Euler graph, because in the Euler graph, we will be using each edge only once, and we will go back to our starting point. Here in Hamiltonian graph, we will be using the vertex or the vertices. Okay? Okay, so this time we will continue our discussion with the weighted graph. Now, when we say a weighted graph, it is a graph wherein each edge is associated with a value which is called as weight. So our aim here is to find the minimum weight, or to provide, all right, to provide a path, a road, wherein it is the shortest way possible. Okay, to find the shortest path, the shortest way. Now, to do that, we have here the greedy algorithm. So how do we apply the greedy algorithm? We have first, choose a vertex to start at, then travel along the connected edge that has the smallest weight. Okay, so we will be choosing the smallest weight. Now again, the weight, these are the values or the numbers that is associated to every edge. Now if two or more edges have the same weight, pick any one. After receiving the next vertex, travel along the edge of the smallest weight that connects to a vertex that is not yet visited. Continue this process until you have visited all the vertices, and then return to the starting vertex. So that means again, we'll be using each vertex once. Okay, so we have here an example of a graph. We have vertex A, vertex D, B, C, E, F, and G. So that is up to you if where you want to start. Now, as for me, I wanted to start in vertex A. Okay, so we will start in vertex A. Now, from vertex A, I have two options. I can go to vertex D, and I can also go to vertex B. But the one with the smallest weight is vertex D, since it's 5 only. I mean, going to vertex D, since the edge here is 5, weight has a weight of 5, and the other edge has a weight of 7. So I'll go to vertex D. Now A to D. Now from D, I have here three options. I could go to vertex D, to vertex E, and to vertex F. Okay? So the edge that goes to vertex F has a weight of 6. The edge to vertex E has a weight of 15. And we have the edge from vertex D to vertex B, that is 9. Okay, so I can have here D to B, which is 9, D to E, that is 15, and D to F, which is 6. So the smallest is 6. Therefore, I will go to the vertex F. Now, from A to D to vertex F. Now, from vertex F, okay, so I have here two options. I can go to vertex E, all right, and I can go to vertex G. Now the shortest or the smallest weight here is from F to E since this is 8 only compared to 11. However, if I will go directly to vertex E, then I will miss vertex G, which is not possible if we will be following the condition because all of the vertices should be used. So therefore, I will go to vertex G. Okay, from F to G. Now, from G to E, I don't have any other choices, all right? So I can only go to vertex E because I cannot go back to vertex F. Okay, from G to E. Now, from E, I have also option E to B and E to C. I cannot use E to F and E to D because I have already used these vertices. So I have E to B and E to C. Now, the edge that has a smaller weight is E to C since this is only 5 compared to 7. So from E, I will go to C. Right? Now, from C, I will go to B. From B, I will go to A. So we have utilized or we have used all the vertices in this graph and we went back to our starting vertex. Okay, now let's try to add the weight in each edge. From A to D, that is 5 plus. Let us suppose this is the distance, okay? From D to F, that is 6. From F to G, that is 11. Okay? From we have G to E, that is 9. Right? From E to C, that is 5. And then we have here from 5, from C to B rather, right? That is 8. And we have here from B to A, that is 7. Okay, so let's try to add this one using our calculator. We have 5 plus 6 plus 11 plus 9 plus 5 plus 8 plus 7. Right, that gives us 51. So this is the shortest way or the shortest path that we can use or that we can find. Now, if you wanna check if this is really the shortest path, then you can also try it. Okay. Now that is how we will be dealing with Hamiltonian graph and a weighted graph using Dirac's theorem and the greedy algorithm. Now, if you do have questions, if you do have queries or any other suggestion, you may comment it down below. And please don't forget to like and subscribe. Thank you and goodbye.